Okay, Matt Roscoe here at the University of Montana, lecture on the history of mathematics, the 19th century in Burton's book on the history of mathematics, chapter 11. Yesterday we took a look at the parallel postulate in attempts to um, resolve the troublesome fifth postulate. Let's go ahead and move on today to talk about the age of rigor. One of the most distinctive features of the 19th century mathematics was a strict logical approach to the study of mathematics. So the universal search for explanation, proof, and logical necessity has led many historians to call this era that of the age of rigor. So to give you an idea of all of these areas in which rigor was being applied during the 19th century, we see an overhaul of the foundations of geometry. Gauss, Bully, and Lobachevsky. The start of the study of non-Euclidean geometry takes place in the 19th century. We see a limit-based logical framework to validate the calculus. So up until this point, calculus had been an obscure set of rules and procedures that seemed to work but didn't have a real logical framework for them. We have D'Alembert, Euler, Lagrange, and Cauchy to thank for that. And then we see the study of convergence take a more logical and proof-based approach. So Cauchy and Fourier. Analysis gets underway in the 19th century with Weierstrass and the work of Kovalevsky. The axiomatic movement of Pauch and Hilbert, and then attempts to generalize arithmetic to other settings by Peacock and Hamilton, which leads to matrix algebra and linear algebra, if you so desire. And then the study of modern algebra, what we think of abstract algebra, in the works of Cayley, Sylvester, and Weber. And finally, Boolean logic gets started in the 19th century, again, from a rigorous standpoint. The two red people that are noted here in this slide are those whose work we're going to take a closer look at. The rest of these figures are, of course, included in Burton's text, and I just ask you to read up on those stories. So let's take a look at Fourier. And in 1822, Fourier put forward in his analytic theory of heat a pretty astounding claim that he could express any periodic function f of x, which was defined on the interval from negative pi to pi and has a period of 2 pi, as some infinite sum of combinations of sines and cosines. The interesting part is that this form is only governed by 3 parameters, a sub 0, a sub n, and b sub n, whose values are found through integration. And so it's an incredibly broad result that allows us to find converging series of sines and cosines that will express any periodic function. Now, if you read the text, you'll find out that Fourier actually was a little bit incorrect, that there are some limitations. Not any arbitrary periodic function can be modeled this way, but let's just say that most can. And read the fine print for that detail in your chapter. But let's take a look at what he did as an example problem. We're going to show, as Fourier did, that the following periodic function can be expressed as an infinite trigonometric series. So there it is. There's a periodic function that meets Fourier's requirements. It's periodic. It has a period of 2 pi, and it's defined from negative pi to pi. And so let's try to see if we can come up with the form of f of x here that Fourier claims will model this particular periodic function. So off we go to the races. Let's take a look at how we go about this, or how Fourier really went about this. So so really what it's all about, we have a form. All we need to know are what the 3 coefficients are, a sub 0, a sub n, and b sub n. So let's take a look first at a sub 0. And a sub 0, we're told, is defined by the integral 1 over pi from negative pi to pi of f of x dx. So let's remind ourselves what f of x is, and remember that it has to be defined on the interval from negative pi to pi, which in this case it is. It looks like that. This is that's positive pi. And that would be negative pi. So, and it looked like on the graph that was given, this was negative pi and this was positive pi. So it kind of looks like, I guess that. And so we can identify what f of x is here by looking at the graph and telling ourselves, well, it's a linear function. It passes through the origin. It has a slope of 1. So f of x here must be equal to just x. So that will allow us then to substitute in here and find the particular a sub 0 that works for this particular periodic function. So what is it? 1 over pi times the integral from negative pi to pi of x dx. And rather than just diving in and doing the integration, I'm going to use a geometric approach and say, well, you know, if you were to integrate this, you'd find that area under the curve, and you'd find that area under the curve, and you'd sum them. And area A would be negative, and area B would be positive, but area A and area B are exactly the same, so the value of this integral must be 0. So it turns out that's the case here, that a sub 0 is indeed 0. And so our first coefficient is actually gone in this particular instance. And so let's go ahead and move on and talk a little bit about a sub n next. Okay, so let's see. A sub n, we're told, is equal to 1 over pi times the integral from negative pi to pi of f of x times cosine of nx. So I'll remind us that f of x is x here times the cosine of nx dx. Looks like this is a integration by parts problem, so I'll remind you of how that works. So if we are going to integrate by parts, we have u dv is equal to, the integral of u dv is equal to uv minus the integral of v du. So in this case, what we probably want to identify as u is x because it's derivative. It's the piece that's kind of giving us a hard time in the integral. So let's see, u is equal to x, so du is equal to dx. So let's see, what would dv be? Well, it's got to be the rest of it, so dv's got to be that. That's cosine of nx dx. So that makes v the integral of cosine nx dx, which is, well, the derivative of sine is cosine, so it must be 1 over n sine nx is our v value. So let's go ahead and rewrite the integral now using what we know. So it's the same thing as the integral uv, or excuse me, the value u times v, so x times 1 over n, so we can write that as x over n sine nx, okay, and minus the integral of v du. V is 1 over n sine nx dx, and that's from negative pi to pi. Okay. Well, let's carry out the integral and find out what we get. 1 over pi x over n sine nx. Let's see. So let's see. The integral of the sine is negative the cosine, but since we've got an argument in here, we'll have to bring it out in front by the chain rule. So I think we'd end up with plus 1 over n squared cosine nx, again evaluated from negative pi to pi. Okay, just a quick check, derivative of this would be derivative of the cosine's negative the sine times the derivative of the argument n times 1 over n squared would be 1 over n, so it does look like it checks fine. Okay, so let's go ahead and evaluate. If we evaluate, we find out that this is 1 over pi times, okay, the positive pi over n sine of n pi plus 1 over n squared cosine of n pi, and then it'll be that value minus 1 over pi times, okay, let's see, evaluated at negative pi, so it'll be negative pi over n sine of negative n pi plus 1 over n squared cosine of negative n pi. Okay, so the first one evaluated at pi minus the second one evaluated at negative pi. And there's some things that can kind of help us here. I can see these are very closely related um, terms. And so let's kind of think about how the sine of x is related to the sine of negative x. So this doesn't fit very well, so maybe what I'll do is put it right here. So how is the sine of x and the sine of negative x related? Well, the sine function is what we think of as an odd function, right? The value at a positive value of x is just exactly the opposite, the value at a negative, that same negative value of x. So we would say that this is equal to the opposite of the sine of negative x. And the cosine's case is just the opposite of that. The cosine is an even function, so we could say cosine of x is equal to cosine of negative x. So, you know, we can use the fact that sine and cosine are odd and even functions to perhaps get some traction here. So let's see if the sine of, if I want to take a negative away from here, or sine a negative here, then I have to sine a negative there. So if I want to sine a negative here, making it positive, I have to sine a negative here, making it positive. So that'll be the same expression according to this equality. And when I look at that, I can see that 1 over pi times that argument minus 1 over pi times that argument, those things go away. They will cancel. So that's my first cancellation. Now let's take a look at the cosine. So if the cosine at a negative value of x is the same as the cosine at a positive value of x, that means we can simply just change that negative n pi to positive n pi and not risk changing the value of that particular argument. So I can see 1 over pi times this minus 1 over pi times that. So cancel, cancel. So it looks like a sub n is equal to 0 as well. And indeed it is. So we've gotten rid of a sub 0 and a sub n. So all the action must be with b sub n. So let's take a look and see what b sub n is supposed to be. And it's 1 over pi times the integral from negative pi to pi of x sine nx dx. So again, we have a substitution that would be helpful here. U dv is equal to the integral of uv minus the integral of v du. Here I would choose for my u my x, so u is equal to x, du is dx. Sine nx dx would be dv. Which makes v equal to, let's see, negative 1 over n cosine nx. Yeah, because it's the derivative of the cosines. Negative the sine, so that'll get rid of that. Negative sign, and then by chain rule, the n will come out and cancel with the 1 over n. So we've got u dv there. Let's go ahead and use our substitution now. It'll be uv, so x times negative 1 over n. So I'll call it negative x over n cosine nx. That's my uv part. And then it'll be, I'm running out of room. Let's do it down here a little bit. 1 over pi negative x over n cosine nx. And then it'll be minus the integral of v du. So let's see, v is negative 1 over n cos nx, and du is dx. And that's evaluated from negative pi to pi. Okay. So far so good. Let's go ahead and notice that we have a negative and a negative here in the integral, so we can call that positive, integrate the cosine of nx, and come to something without integral signs here. Negative, x over n cos nx. See, the derivative of the sine is the cosine, so it looks like we'll have 1 over n squared sine of nx, and that'll be evaluated from negative pi to pi. Okay, so let's see what happens when we try to evaluate this. I think I'm going to go ahead and switch to a different one. So when I evaluate it, I get 1 over pi times, let's see, when I put pi in for x, I get negative pi over n cosine n pi plus 1 over n squared sine of n pi. Okay, and then I will subtract away 1 over pi times the evaluated function at negative pi, so it'll be a negative pi, so that'll be a positive pi over n cosine negative n pi. And then let's see, plus 1 over n squared times the sine of negative n pi. And now let's play some games again with what we know about sines and cosines. So I know that cosine is an even function, so it doesn't matter if it's a positively or if it negatively evaluated argument. They're the same, so I can simply change that. The exact opposite is true for the sine. So if I change this to a positive, then I have to change this to a negative. And I can go ahead now and combine some like terms. I can see that I've got a pi over n cosine n pi here that's negative, and the same thing here when I distributed the 1 over pi. So it looks like, well, pi's will cancel. I'll get minus 2 over n, minus 2 over n cosine n pi. And then for the sines, let's see, I get 2 of those as well over n squared pi sine n pi. Okay, so we've got some sort of a closed form here. But I want to make a quick note here that recall that in the Fourier transformation, n is an integer. And so when n's an integer, what we have here is some multiple of pi for the sine argument. Oh, and the other thing is n is greater than or equal to 1, so it can't be 0. And so any multiple of pi, the sine evaluates at 0. So what can we say? This guy, the whole thing is going to go away because of that fact. So we can say that for integer n, b sub n is negative 2 over n cosine n pi. Okay, we're getting somewhere now. Let's go ahead and move that up a little bit and just take a look and see what we get for first few terms of b. So b1 would be negative 2 over 1 times the cosine of pi, right? And the cosine of pi is negative 1, so we would get 2 over 1. Let's try b sub 2. That would be negative 2 over 2 times the cosine of 2 pi. Well, the cosine of 2 pi is now positive 1, so we get negative 2 over 2. B sub 3 is going to be negative 2 over 3 times the cosine of 3 pi, and the cosine of 3 pi is negative 1, so we get 2 over 3. And now I can kind of see what's going on. The 2 on top stays. Of course, that's coming from there. The n on bottom is simply the subscript n, and the cosine alternates between positive and negative. So b sub 4, what I would expect this to be would be negative 2 over 4, and so on. So the question is, how do I find a closed form value for b sub n? Well, I know that it's going to be a negative 2 over n with a sign, sign adjustment, and the way you can do sign adjustments, of course, is to include a power of negative 1, and the right one is to include negative 1 to the n. Just check it. If you plug in 1 here, you get negative 2 times negative 1, which leaves you with a positive 2 and 1 in the bottom. So this is our b sub n coefficient in the Fourier transform. Let's go ahead and carry out the transform and finalize our result. So the result for Fourier gives is this. He says, you know, I can model any periodic function this way. It's 1/2 a sub 0 plus the sum n from 1 to infinity of a sub n cos n x plus b sub n sine nx. Okay, and what we found in this case is that this is 0, and we found that this is 0 as well. So really all we're worried about is the sum from 1 to infinity of b sub n, which we're going to call negative 2 over n times negative 1 to the n, times the sine of nx. So just to write out a first few terms here, the first term would just be 2 over 1 times the sine of 1x. The second term would be negative 2 over 2 times the sine of 2x. The third term would be, let's see, so positive 2 over 3 times the sine of 3x, and so on. So the way the book gives this is they say, well, pull the 2 out, and what you have is sine of 1x over 1 minus sine of 2x over 2 plus sine of 3x over 3, and the signs alternate, and on we go. And so this should be the infinite sum that leads to the model that Fourier claims he can construct for the periodic function that was given. Let's go ahead and see if he's right. So I'll escape out of here and minimize and remind you that this was the picture we were looking at, and pull up that picture in GeoGebra, hopefully. There it is. So if you look closely, you can see that what I have here are 3 lines that are indicative of the periodic function that the transformation is trying to model. And here I have just the first term in the Fourier sequence that we just generated, 2 sine x, and you can see it's a pretty poor fit. But of course, if I adjust with this slider to get to the next term, I can see we're getting a better fit. And if I add a third term in, even a better fit, and a fourth term, and a fifth term, and a sixth term, and a seventh, and eighth, ninth, and 10th term. And if you push this little player button in the bottom, you can watch it converge. And of course, what we're looking at is the convergence of an infinite series of sines and cosines, at least out to the 10th term, to a general periodic function. And I think it's a pretty amazing result, and it certainly shows some in-depth understanding of convergence in this particular setting. So I invite you to explore the Fourier Explorer that I'm looking at here in GeoGebra. It's available on the website in our Moodle resource. And I will tell you that you have one Fourier transformation problem in your homework for this week. That one is number 2, problem number 2 in section 11.3. If you complete that and show it to me on Monday that you've found the correct version, and especially if I can see a picture of it using some software, I'll give you 2 points of extra credit for, I should say 2 points on the last quiz added to your last quiz score. 1 point for doing the work and 1 point for some sort of a picture of it using some sort of software. This particular software would be just fine, GeoGebra, or if you prefer some other software like MATLAB or Mathematica to produce the picture. Okay, well, have a good weekend. I look forward to seeing you on Monday, and we will talk then.